For today's lesson, we are going to talk about quite an interesting topic known as momentum and collision. And I'm sure you are as excited as I am to know about these terms. A moving body has the property which causes it to exert force on any body that attempts to stop it from moving. The faster the speed of the moving object, the more difficult it is to stop it. And the heavier the object, the more difficult it is as well. This is why it is very difficult to try to physically stop a moving aircraft than a moving car. In fact, even Superman would need to put in more effort to do this. This property of a moving body is known as the inertial momentum. But what exactly is momentum? This word, momentum. Momentum, P, that is the symbol for momentum, is a measure of how difficult it is to alter the motion of an object. A fly, flying at 20 meters per second. Let's say we have a fly now, flying at 20 meters per second. Now, it has a less momentum than a car moving at the same speed. Also, a heavy tanker moving at, say, the same speed has a greater momentum than a similar tanker moving at 10 meters per second. So technically speaking, momentum is defined as the product of, so momentum P, the product of mass times the velocity, times velocity of a system. The plural of momentum is simply momenta. So when you see this term, do not get confused. It's still momentum. In other words, the more momentum an object has, the harder it is to stop it, and the greater effect it will have if it is brought to rest by impact or collision. Note that momentum is defined with respect to velocity and not speed, because it is a vector quantity. And from its definition, we can have its units to be, so the unit of momentum, is kilogram meter per second. This is the unit for momentum. The momentum of a particle is related to the next force on that particle. How? This is because a force is required to change the momentum of an object, whether it is to increase or decrease the momentum, or change its direction, according to Newton's second law of motion, which we know to be F equal ma, right? Now, A is equal to change in velocity, right? Change in velocity. A is the acceleration, take note. Change in velocity over change in the time, right? And we can as well write this as A equal dv over dt. You agree with me, right? Now when you put this back into this equation, let's call this equation now A. And when you put this back into the equation A, you have that m equal m dv over dt. So we can as well write this F equal dm mv over dt. Okay, now we can move m inside the derivative because it is a constant. Alright, now what do you notice in this new equation? Let's call this equation b. You can see that mv is momentum p, right? From our definition of momentum. So if we put this knowledge back into the equation b, we have it to be F now equal dp over dt. As simple as that. Okay, so this equation that we just got is even more general than our familiar F equals ma that we know. We usually make reference to this equation as the Newton's second law of motion, right? So now it creates an allowance for a situation in which the mass may change. So this is one of the reasons why this particular equation now is more familiar. Alright? With this, we can say that Newton's second law can also be stated as the time rate of change of objects, momentum, is equal to the resultant force acting on the object. Note this. When a particle moves freely, then interacts with another system for a brief period, and then moves freely again, we can say it has a definite, that is, specific change in momentum. And we define this change as the impulse. I'm sure you must have come across this word, impulse. Now, impulse is represented as I. So we define this change as the impulse I of the interaction forces. So I, that is impulse, can be given as change in momentum. So I say change in momentum from P2 minus P1, or we can say PF minus PI, which is the final momentum minus the initial momentum. And so we can write this too as this means dP. You agree with me, right? Because P2 minus P1 is simply the change in the momentum. Now, if we relate this back to our first equation, okay, let's call this equation C for easy reference, okay? From the definition of impulse, if we put it back into equation C, what do we get? We can write equation C now as F equal impulse I, which is seen as a change in the momentum, right? Over dt. Now, when you cross multiply, we can get impulse again at I to be F dt. And this F dt can be further written as I equal F T2 minus T1, which is the final time minus the initial time, okay? Always take note of that. We can also write this as, impulse is the change in momentum, right? So we can write this to be P2 minus P1 equal F in bracket T2 minus T1. This is still the same thing, just different ways of writing them. So we've been able to relate impulse to the momentum. So this result here is termed or called the impulse momentum theorem, which states that the change in momentum of a particle during a time interval equals the impulse of the net force that acts on the particle during that interval. Impulse is a vector quantity and has the same unit as momentum, which is kilogram meter per second. We are not done yet. Hang in there.